Hello, my name is Amanda, and I am here again to answer more questions from my students. We are talking about confidence intervals, and um, there's a description in the book that goes through how they're formed and how you can use a formula to make a confidence interval. And what I want to do is give you kind of the idea behind it so that you can see what would happen when I'm making a confidence interval. And so I have here um, I went to the World Health Organization and I pulled, they have this global health observatory, and I downloaded some data on maternal and reproductive health. And I have a whole lot of stuff down here. And I thought, why not? Let's go and pick one of those. So if I pick pregnant women hemoglobin data, don't ask me much about what that means, but I've got it. And I'm going to call it hemoglobin. And so I've got hemoglobin, and I'm going to read that up. And then I want to know, what's in there. And so I've got now hemoglobin. I have the code, spatial dimension, a whole bunch of things here at times. Eventually I'll get a hemoglobin level, which is down here. And so I've got this value, and then it actually reported it as a confidence interval, which is a little bit funny because we're talking about confidence intervals. But I'm going to pick the numeric value. And so and you do a new block. I'm going to do hemoglobin numeric value. And I want to get a quick summary of that just to make sure that it looks nice. So the smallest is 103, the max is 124. Everything's got it clustered in the middle between 113 and 119. I don't have to get rid of any outliers for these data. Sometimes I've got outliers running around, and then like this would be a quick way to see if I need to kill any. But these don't have any outliers. If I had data that had outliers, like if this was 5, then I would have to decide if I want to get rid of it. Okay. So the idea for confidence intervals is that I take my thing I care about, the hemoglobin numeric value, and I'm going to pull a sample, and I'm making sure that everything I pull out, I'm putting back in before I pull the next connection. And so I'm taking a sample of 1,000 values that are hemoglobin levels, and then I'm averaging it. And I do that, and I get 115. And I do it again, and I get 115.48. And I do it again, and I get 115.42. And I do it again, I get 115.501. So I'm thinking 115 is like a very common number. If I do this a lot, every time I do this, I can like plot it on a graph, and I'll just get a whole bunch of numbers. And I want to do that and keep track of it. And so that's where I get these collected averages. So I'm going to initiate a collection and a counter. And so this is where I'm going to store my information. And then this is how I'm going to count how many things I'm going to do. And I'm going to make a for loop. And I can decide how many times I want to click this button. Right? Do I want to click that button 1,000 times, 10,000 times, 100 times? Let's go with 10,000. And I'm going to make collection part I to be what I get when I put hemoglobin numerical value. And then I do like this exact thing. So like if you're copying and pasting, you would just copy this whole thing and it would go there. And then after I gather it together, I'm going to send out a summary. And so I did 10,000 times, sample it, and then save it. And then this is the summary of all of those. And if I do it again, I'll get a slightly different summary. Like you see my max move to 116.1. And I do it again, and I get a slightly different summary. My min moved to 114.9. So every time I do it, it's slightly different, but they're all generally between 115, 116, with that middle always like 115.5. And so there's this idea that if I make this happen a lot, where I'm clicking this button 10,000 times, everything kind of converges on this one spot. So to see it, I'm going to take the collection list that I put together. I'm going to make a cumulative distribution function because that will tell me how much of my data lives at or below different points. And I'm going to make a density collection for it so that I can figure out how often different numbers show up. And I'm going to pull those things together in this new distribution. And so this distribution will take the averages from when I was up here clicking these buttons, and then the density using my collection density function on what I had before, and then the actual density, which gives me the how often things show up. And then this is where the confidence interval part shows up, because I have to decide, like, what is your confidence level? So if I want to be 99% confident, then I want to save 99% of my data, which means I need to go from, like, I have like 1% split top and bottom. So I need to go from 0.005 to 0.995. Like, those are the outsides. And then I can hit play, and this is going to shade in that middle section blue. And so I've got 99% of my data here shaded in blue. It's smooth like this because I use that density function here, and that's what I'm graphing, is that density function. And the this part here, where we saved the middle of that distribution, or I'm filtering it between this number and that number, you can find the minimum of those and the maximum of those. And it'll give me 115.09 and 86. And so I am, like I said, 99. I am 99% confident that the average hemoglobin level of pregnant women is between 115.09 and 115.86. And I don't know what units we use for hemoglobin levels. And so that's how you bootstrap it. If I wanted to look for, say, 95% confident, then I've got 5% to split top and bottom. And so this will be 0.025 and 0.975, because I've got my 5% split. And I hit play on that one. And you can see that it got narrower. Then my bound switched. Oops. Click the wrong button. My bound switched so that I'm now at 115.17 and 115.736. So I said 95. I could copy and paste this. Between 115.18 and 115.76. Period. So I'm 95% confident that the average hemoglobin level of pregnant women, misspelled pregnant, is between 115.18 and 115.76. So I can just change what my middle filter picked using my cumulative density function and then get a new one. And if I wanted to compare that to the formula, right, remember there's this t-test command in R that just uses the formula from the book. I would do, this is my hemoglobin average, no, what did I call it, value? Numeric value. And my confidence level this last time was 95%. I play there. Oh, they got mad at me. I forgot my comma. I am 95% confident that the average hemoglobin level pregnant women is between, this time it's 115.33 and 115.62. Right. So these numbers are different because this one used the formula and this one used randomness. And so it depends on what scenario you're in to say like which one will be preferred. Most of the time, your data are big enough that you can just use your formula, and then that'll be fine. The confidence, the bootstrapped version works when you have smaller data where the formula no longer works. But that's what's going on with confidence intervals, is that I've averaged, like I hit play on this averaging a billion times. I collect them, and then I graph them, and then I'll get a confidence interval based on that graph. And so this one was 95. And at 95% confident this time, I got 115.19 and 115.76. And so it's close, but not exactly the same. I can make these match slightly better if I make the sample size match the data size. So like over here, I've got this 40-40. When I hit play, it's going to take a little bit longer because I've got 4 times as much data running around. And play and play. This time I got 115.33 and 115.62. And down here, 115.33 and 115.62. Hey, look at that. And so if I took the time to make the sample match the sample size when I'm simulating, then you get the formula matching the bootstrap pretty well. All right, so that's the basics of confidence intervals, where you can play around. See you on campus.